Functions are increasing in intervals where the first derivative is positive. Functions are decreasing in intervals where the first derivative is negative. To locate these intervals, mark the critical numbers of your function on a number line and test numbers around them in the first derivative to see if your rate of change is positive or negative. Given the function negative 3x squared plus 12x, the graph is over here to the right of your screen. Let's find the first derivative and the critical number. Note this graph only has one hill, so we only expect one critical number. Our first derivative is negative 6x plus 12, and that's equal to 0 whenever 12 equals when 12 equals 6x. I brought it over and added. Divide both sides by 6, then you get a critical number of 2. Where the x value is 2, that's where the top of the hill occurs. Now, we're going to mark that critical number 2 on a number line and test surrounding numbers in the first derivative. So on this number line, and this towards the bottom right of your screen, I've marked off the 2, and then I pick a number smaller and a number larger, test these numbers in the first derivative, which is negative 6x plus 12. So if you test a 1, negative 6 times 1 plus 12 is 6. That's positive. And since that's the first derivative, we have a positive rate of change, or increasing. The test number on the other side of the critical number, we picked a 3. Negative 6 times 3 plus 12, that's negative 6. And since that's a negative rate of change, our function is decreasing on this interval. If you look at the graph at the top right of your screen, you can see that the graph increases until you get to your critical number. After your critical number, the function decreases, which matches our first derivative test. As far as the intervals go, your cutoff number will be the dividing number for your intervals. So this function increases from negative infinity until you get to your critical number. After you get past your critical number, the function decreases from 2 to infinity. And that's how I get my intervals. Negative infinity to the critical number, and then critical number to infinity, increasing and decreasing. Given y equals negative x cubed plus 12x, find the first derivative in critical numbers. For this one, we have negative 3x squared plus 12 as our as our first derivative. Setting that equal to 0, we can factor out a negative 3 from these two terms. If we factor out a negative 3, that leaves x squared minus 4, and you can redistribute to check. That's still negative 3x squared plus 12. So it's factored correctly. In the parentheses, we have a difference of 2 squares, and that'll break down as x plus 2, x minus 2. Since negative 3 doesn't contain a variable, we don't worry about it. It won't contain a critical number. These other two factors will. X plus 2 is equal to 0 when x is negative 2. X minus 2 is equal to 0 when x is positive 2. We have two critical numbers, and if we look at the graph to the right, we have a valley and a hill. That's a total of 2 critical numbers. Marking negative 2 and positive 2, we get this point at the bottom of the valley and this point at the top of the hill. Now we can tell by looking at the graph that we increase between the criticals, and then decrease again. Let's make sure that our calculus backs that up. Remember, our first derivative is negative 3x squared plus 12. So as we progress through the problem, I'm going to mark the critical numbers of negative 2 and positive 2 on this number line. We have to pick test numbers between and around those criticals. A convenient number between the criticals would be 0 or 1. In class, we chose 1. A number smaller than -2, we picked -4. A number larger than +2, we picked +4. Since we're looking for increasing or decreasing, those are rates of change, we plug those into the first derivative. When you plug -4 into the first derivative, you get an answer of -36. So that's a negative rate of change left of the first critical number. The test number between the critical numbers gave us a positive answer. So that means we're increasing between the critical numbers. And then finally, the test number to the right of the second critical number, we picked a 4. The rate of change at 4 is negative, so that tells us our function is decreasing. If you look at the top right of your screen, you can see that our math and our picture match up pretty well. Decreasing till we hit our first critical number, increasing between the criticals, and then decreasing after the second critical number. Putting this in interval format, increasing between the criticals, -2 and +2, decreasing left of -2 and right of +2. Given the function x² plus 8x plus 16, the graph is to the right over here. Our first derivative is 2x plus 8, and that derivative is equal to 0 when x equals -4. -4 is our critical number, and if you look at the graph to your right, the x value -4 is in fact where we have a valley floor. Marking -4 on a number line, testing left and right of it. In class, we decided to go with a -8 and a 0. -8 plugged into your first derivative gave a negative answer, so our rate of change is decreasing. The test number to the right of the critical, we picked 0, and that's always a good choice. 2 times 0 plus 8, again, this is in the first derivative, gave us a positive value, so we're increasing. Increasing left of the critical, decreasing left of the critical, increasing right of the critical. If you look at the top right of your screen, we decrease till we hit the critical, and then we increase afterwards. And then our intervals, that's just going to match. We increased to the right of our critical number, 4 to infinity. We decreased on the left side of the critical number, -infinity to -4. And then we're also challenged with finding a relative minimum. This one has no relative maximum. Let me go back to the graph because we don't have any hilltops. Whoops, sorry, y'all. We don't have one with a hilltop in it. This one's strictly a valley. So all we have is a relative minimum. Now what a relative minimum is it's the actual point at the bottom of the valley. Because we're looking for the point of the original function, use the original function and your critical number to get the y-coordinate of your relative minimum. So plugging the critical number into the original function is going to give us -4 squared plus 8 times -4 plus 16, and that totals out to 0. The number you plug in and the answer you get paired up forms a point on the original graph. So I'm going to go back up one more time, and we will note that -40 is in fact the lowest point on that graph. And so that's a relative minimum. Let's do one more that's very much related to the last example we did. Let's take the function -3x squared plus 2x plus 7. the graph of it is over to the right. Now this one is shaped like a hill. Since it has no valleys, we don't have to worry about finding a relative minimum. We'll actually find a relative maximum at the end of this one. All right, so same game plan as we've been doing. We'll take our first derivative, which is negative 6x plus 2. Negative 6x plus 2 is equal to 0 when x equals 1/3. So what I did was I took 6x across and added it. That left 2 equals 6x. Divide off the 6. 2 over 6 reduces to 1/3. This x value of 1/3, that tells us where the hilltop is going to occur. Mark 1/3 on your number line. Pick a test number smaller than 1/3, a test number larger than 1/3. In class, we pick 0 and 1. 0 subbed into the first derivative gave us 2, which is positive. So we're increasing on the left side of the critical number. We picked 1 as a test number that's larger than 1/3. The first derivative with 1 subbed in tested negative. So decreasing on the right side of the critical number. If you go back up to the top right of your screen, all that matches. Increasing until we get to the critical number, decreasing afterwards. The interval of increasing is negative infinity to 1/3, negative infinity to 1/3, which is our critical. The critical number is the cutoff for these intervals, by the way. Decreasing after the critical number, so that's 1/3 to positive infinity, we're decreasing. This one, because the original graph is shaped like a hill, does not have a relative minimum. It will have a relative maximum, and that is the point right here at the very top of the hill. Now, in order to get the y-coordinate, we plug the critical number into the original function. So we have f, the original f of 1/3. Substituting in to the original function, we have negative 3 times 1/3 squared plus 2 times 1/3 plus 7. In class, we typed this into our calculator, and then we converted our answer back to fraction form. If you type this in and just hit enter, you're going to get 7 point and a whole lot of threes. That's 7 1/3, but WebAssign likes fractions. So once you type all this in, if you're using a calculator, there's usually a convert from decimal to fraction. If you use a graphing calculator, hit your math button and then hit enter twice, and it'll convert your decimal to a fraction. If you're using a smaller scientific calculator, look for the button that has a double-headed arrow from D to F, and that's converting back and forth from decimal to fraction. Long story short, the critical number is your X value. The answer you get pairs up with it at your Y value. And when you go back up and look at your graph, this point is the relative maximum, and it is 1/3 and 22/3 as the coordinates. I hope this video has helped out. You guys feel free to reach out by phone or email. Give me a call if you need to. And if we have class together, for sure ask in class. I hope this video helps.